totally enough for exam. About this chapter, phase diagrams, well, I'm not gonna go through like every concept, so just a quick review. But I don't know, just let me know if you have any specific question.
The last exam, where it's just basically scribbling.
Yes.
It's all out of conceptual stuff.
Yeah. Yeah, it's all calculation stuff, very similar to assignment. So this chapter was about the phase diagrams. So the main concepts here, like the solubility limit and finding like the percentages of solid, liquid, different phases. I'm assuming you already know all those things. Yeah, these are like the basic phase diagrams. And you have this lever rule. Yeah, this is like the weight percentages. Let's see. Yeah, we also reviewed, we discussed the structure of the phases. And like these terminologies are also important. Should know what's the eutectic, eutectoid, hypereutectoid, those things. So this one is a long chapter. Yeah, we also discussed the iron carbon phase diagram, actually the steel phase diagram. So it's all about the phase diagrams. Do you have any question from this chapter? So phase transformation is kind of like a follow-up on the previous chapter. It's very related to phase diagram. So the main thing we discussed here was like supercooling of metals and this homogeneous nucleation. We introduced this heterogeneous nucleation, but we didn't like focus on this. So we had a couple of formulas about this homogeneous nucleation. Yeah, like this stuff. That's like the critical radius for the nucleation. What else? Let's see. And from the equation, these are all about the homogeneous nucleation. And we also discussed like transformation, phase transformation about the steel. We talked about this diagram here, paraloids, and all these other phases, how they transform. So review this stuff again, and just take a look at the assignments. Any specific question about this chapter? Okay, so let's see chapter 11. So this is also about metals. about applications and some mechanical properties. Cast iron. So introducing different types of iron and characteristics. Yeah, the main thing about this chapter is that the code working processing. Yeah, this chapter doesn't have a lot of like calculation stuff, but it's still good just to review. And well, ceramics. Basically, like this is chapter 12. Chapter 12 and chapter 13 are about ceramics. First, we talked about atomic bonding in ceramics, and let's see, charge neutrality. We introduced different structures, like common structures, based on this ratio here. And based on that, we had some questions. So it's also good to know these structures, like rock salt structure is one of the most discussed in this chapter, and it's one of the most common. Yeah. Well, yeah, we can go over any like problems or questions. No, it's okay. I mean, that's the purpose of this session. If you have like any questions, I don't know about those questions, but if you like having difficulty solving any of those, yeah, we can go over. So I'm just gonna quickly, I guess, so we already talked about this. But, well, yeah, I'm gonna quickly just go over the remaining chapters, and then we can discuss any problems you have. But again, the problems is gonna be very similar to the homework and to the problems you also solved in this class. recitation sessions. Well, so about this chapter, let me know if you have any question about this chapter so far. Well, this is like one of the formulas in this chapter, calculating the density. It's fairly easy, nothing crazy about it. And for the homework in this chapter, there was like a question asking to find the angle and those stuff, but that's not going to be in the exam. So don't worry about that. And the vacancies is the other important concept of this chapter. You had like formulas for these type of defects. And finally, we talked about mechanical properties. So, main thing about ceramics, we talked about mechanical properties, vacancies, densities, and like the radius, ratio, and type of the different ceramic structures. Those are the main things about ceramics. And for the application, I guess that was like a short chapter, didn't go through a lot of application, just a very quick review. It's more like an introduction to different stuff. We talked about this viscosity. Just the rest of it, just introducing different things like different fabrication methods and different properties of ceramics. So this chapter is also very short and just to test that viscosity concept about the ceramics. The next is about polymers. So first we introduce the polymers here. It's a little bit of background of polymer. So you don't have to know like these different structures, don't worry about that. And these are again just terminology, but it's good to know like unsaturated and saturated. So unsaturated basically has double bond or triple bond. Saturated is only single bond. Talking about polymerization, just for your knowledge. So again, the main concept about the polymers is this molecular weight. We talked about molecular weight in details. We introduced two different ways for showing the molecular weight: number average and weight average. So you should know them. And degree of polymerization, which is related to molecular weight. Molecular structure is just introduction. Yeah. So this chapter, the main topic is the molecular weight. The rest is good to know, like the structure, crystallinity, and the rest of the stuff, like different types of polymer, linear, chain, local polymer, those stuff. And chapter 15 is about the application and properties of polymers. So let's see what we have here. I guess we talked a little about the mechanical properties here. Yeah, basically is the mechanical properties like the stress strain behavior in polymer. And it's a pretty short chapter, so it's good to take a look at it. I guess it has just few questions, so review those questions. Yeah, nothing complicated about this chapter. Something. So yeah, this chapter was mostly like, introducing different properties and technology for about the polymers, not a lot of formulas. So we're gonna go to the next chapter, which is composites. And here we talked about, well, first we introduced composites. We talked about, we have two main phases, matrix and like a fiber phase. And based on that, we talked about the mechanical properties of composites. So, like how we calculate the Young's modulus and other properties. Like the effect of fiber lengths. And the relationship between the volume fracture, friction, and the Young's modulus. And the stress behavior. So main thing about composite is like the mechanical properties or stress strain behavior of composites. You should also know about those stuff, and basically that's it. So questions like from homework or doing it today, hopefully, or tomorrow.
So there's just no need to worry about anything past chapter 16.
Wait, isn't that supposed to be chapter pass through 18?
We have to avoid the plus. There was a question in the assignment in Biology class asking about like silicate structure, or remember correctly, and it was asking to find like a specific angle. So don't worry about that. I know like some students struggle in solving that, so don't worry about that.
On the screen
What?
that we did in the earlier recitation. So the problem reads, consider 2 kilograms of a 99.6 weight percent of iron and 0.4 weight percent carbon alloy that is cooled to a temperature just below the eutectoid. And they want to know how many kilograms of what's eutectoid ferrite form, and essentially the same question for the eutectide ferrite form and cementite form. So for part A, the first step is you want to determine the mass fraction of the eutectoid ferrite that forms, and that equation should be this it should be your W alpha Barnum equation. I'll check in here. Oh, this one. So to figure out the eutectoid, yes, ferrite mass fraction, you use this formula here. And so each of those values that we put in, let's see. So the 0.76 is essentially like a given value, but your original composition, that value you would put into, you put the 0.4 in here. That's going to be your C naught prime. And essentially you just plug it in to that equation that I was pointing out earlier, and you should end up with the 0.49. And then now after that, you would take that 0.49, multiply that by the mass that's given you in the problem, which I believe is, yes, the 2 kilograms, and then you will end up with the, essentially the mass for that, that phase, or that form, I should say. And essentially we do the same thing again for part B and part C. But for part B, it will be for the eutectoid ferrite, which should be, so I put the eutectoid ferrite, so it should be, I'm wondering if eutectoid ferrite, I'm not sure if I put that one in there. Yeah, I think it's in there. That should be in text. But essentially this is the formula here for that one. I'll put it in orange. So for the eutectide ferrite, to figure out the level for that one, that's this equation here. And essentially you do the same thing. So the 6.7 I believe is the given value for the that phase, the iron carbon phase. The 0.4 again is coming from that 0.4% of the carbon. That should be there. Is it? Here's the carbon phase diagram. This is the
So basically, in that question, we are here, right? Because it says 0.4, so we are before this. You take to a point. So we are in this region, and the first question was like, you take to it, which means like the amount of alpha phase is formed in this region before we get to, because we are cooling down. We are starting like somewhere hot and cooling down at the room temperature. So we enter this part of the diagram, right? And the rest is just the level. For example, let's say we end up at a point here. So you just draw the tie line, and based on that, do the calculation. You're gonna have like, for example, that much alpha and that much is cementite phase. And in total, we had like in the question we had 2 kilograms. For example, if we end up with 1.5 kilogram of alpha, it means the rest is going to be cementite, half a kilogram of cementite. But some of that alpha is the eutectoid alpha, and some of it would be pro-eutectoid. So, it's here. So this, I'm assuming this thing is here. So this lamella structure, that's the eutectoid structure. So these blue lines are like the eutectoid alpha. But the pro-eutectoid alpha is this thicker blue you understand what I said, right? Like before you enter this region, you have some alpha phase here. Those are pro-eutectoid, and the remaining is gonna turn into like a lamellar structure. Those are eutectoid structure. Any question? All good? You're gonna have the diagram itself, but not like the structure. I'm just saying, like, what does it mean when it says like pro-eutectoid? It means the alpha phase that has been formed before entering this region. And eutectoid is the alpha or cementite which is formed after entering this region. And the rest is just a calculation. You do the lever rule like you have it here. For example, we call it, I don't know what he said. Let's say 6.4, which was like the carbon percentage in our question. Then based on that equation, you can get that W alpha, which means that's the alpha, like pro-eutectoid alpha. But at the end, these are the calculation, is like the total alpha. Pro-eutectoid plus the eutectoid alpha.
And I believe so. And then based on like, because there are some like predetermined values already here, like let's see what like 2.3 or I think 0.76 is one of those values too. So those are already values put in there based on, I guess theoretically like when you start to see the phase change, I believe it is. So for example, like the carbon alpha, I think you solve for that one using the equations that were just shown earlier in that one. and that's where you get the 0.022 from. And then for part C, essentially the same thing. So are there any other specific questions you guys have from basically chapters 9 all the way to 16? You want to keep going over like chapter 19 or just like a different chapter? Maybe you guys had issues with homework or something? No questions, right? Everybody's good? Okay. All good, all good. Okay, so let's jump back into chapter 19. Like 15 minutes left or something like that. Okay, so chapter 19, question, or this question here, number 1913. It reads, to what temperature must a cylindrical rod of tungsten, 10 millimeters in diameter, I do not know why they put all those zeros at the end, that's kind of weird, 10 millimeters in diameter and a plate of 316 stainless steel, has a circular hole which is 9.98 millimeters in diameter, must be heated for the rod, or, well, how did I put this one? Yeah, so basically to what temperature do I need to heat up the plate, I believe, to fit the tungsten rod? And they're both two different sizes. And they want us to assume that the initial temperature, I'll assume again for both of those, is room temperature. Okay, so it wants us to figure out the temperature in which the cylindrical rod of tungsten, which is 10 millimeters in diameter, so we're getting the tungsten to just fit into the hole in that steel. And we're starting at room temp. And so the equation that we need to refer to is this one to determine the diameter. So we have, is this one? Yeah, this is one of those where I don't think they really mentioned it in the last one, but so essentially the change in diameter divided by the original diameter is going to be equal to that coefficient of thermal expansion multiplied by change in temperature. Oh, well, that equation is basically this one that we did earlier. But instead of length, it's just that one. Okay, so we have that, and we want to solve for the final diameter that we need, so we can just break this down further so that it reads like this. Yes, so manipulating this equation so that we can get the final diameter by itself. We should end up with something like this. Okay. this point, it is be useful to establish the expressions for the stainless steel and the tungsten, or so the final diameters for both of those. And then set them equal to each other. And then we also want to differentiate between the final, or actually, I'm sorry. Yeah, set those equal to each other and then solve for the final temperature. And also quickly from the table 19.1, the alpha L for the steel should be this. The alpha L for the tungsten should be this value here. Okay, so we know that. Essentially what I was talking about before is we want the final diameter of the steel is essentially going to be the same diameter as tungsten because we want them to fit into each other or fit into the steel. And yeah, then from there, I really like this because at that point it's just you just kind of plug in the values and then solve for TF. I don't solve for TF. I see. Yeah. So you have the steel on one side. Actually, right. So the final diameter of the steel, which is equal to basically all this. Celsius, and that is going to be equal to the final diameter of the tungsten, which we know is going to be 10 millimeters. The coefficient of expansion for that was 4.5, so that's -6. And then we also multiply that by Celsius. And so from there you just solve for the final temperature. And the final temperature HCF for this problem specifically is 29.5 degrees C. Okay, so to recap, this is the equation. So this equation that I used is essentially this guy. But instead of length, we use diameter. You need to find your coefficient of expansion for steel and tungsten from table 19.1. Manipulate it so that you figure out what the final diameter is, and then once you know what the final diameter is, you essentially set the final diameter of the steel equal to the final diameter of the tungsten, and then from there you can solve for the final temperature that would be required to fit the tungsten rod into the hole. So, any questions on that one? Okay, for the next one, so the problem reads, railroad tracks made of 1025 steel are to be laid during the time of year when the temperature averages 10 degrees Celsius. If a joint space of 4.6 millimeters is allowed between the standard 11.9 millimeters long rails, what is the hottest possible temperature that can be tolerated without introduction of thermal stresses? This might be the last one that we can cover for today, so let's see. And there's still a couple more. Yeah, so there's like 3 more on this one. The hardest one was so not this last one, but this guy here. So of course we got that covered today, but I think the other ones, we should be good on those. Yeah, this one's pretty straightforward. So in this problem, the railroad tracks, each end is allowed to expand 1/2 of the joint space distance, or the track may expand a total distance of that 4.6 millimeters that was mentioned here. And so the equation that we're going to use to figure out the highest possible temperature that can be tolerated without introducing thermal stresses is going to be this guy here, which I think is just, again, like this formula here, but we're just manipulating it so that we solve for the final temperature. So we have delta N divided by alpha L, L naught plus T naught. And the alpha L for this problem, for this steel, this is 1025 steel. They keep referring back to table 19.1. I'm not sure if it's like divided into all these different steels or if it's like generic steel. But if you need those coefficient of expansion values, I'll just go back to that table. And that value here is 12 times 10 to the 6 inverse degrees Celsius. And I mean, for the most part, this the values here are all basically given. Let me double check first. Yeah, so the 11.9 millimeters, or sorry, 11.9 meters is the original length, and we know change in length is going to be that 4.6 millimeters. The alpha L, we wrote that down, and then the original starting temperature is given in the problem, which is the 7 degrees Celsius. So if we plug all those in and calculate it, we should end up with 32.2 degrees Celsius for this problem. After that, we're kind of fast, but everything was pretty much given for this problem here. Any questions on this one? Questions? Yeah, good. Unfortunately, we only have like 3 minutes left, and I don't think this next one's gonna be a 3-minute long question. I think, so number 11 was definitely the hardest question to go over. I think the others should be okay. If you guys have questions on these other ones, we can definitely go over them next week during office hours, or if you want me to just go over them for next week's presentation, we can do that too. We also plan to go over basically the last chapters for homework as well in the next presentation, basically after final exam. And after that, we should be good with the semester, I guess, in general. Because we'll have all final exams and stuff and homework and all that good stuff. So yeah. Any other questions, like exam questions or like questions on this stuff? In that case, that's all we have, all we have for you guys for today, and we'll see you guys next week for exam and recitation.